Hello everyone, I am Pushpita Chanda. I am a PhD student at IIT Delhi under IIT Delhi and University of Queensland Joint PhD program. So I am a TA for the course Introduction to Lasers and Laser Systems. So this is for week 5. So let us get started. Okay, so as I have discussed in the last tutorial that I had started the discussion of polarization and there are different kind of polarization, like depolarization and despolarization, and on the basis of how the electric field moves in the plane, it can be dependent on linear polarization, circular polarization, and elliptical polarization. And I have also discussed the concept of Brewster's angle, the angle at which the reflectivity of the p polarized light is basically zero. That means if the light is constant of S polarized light and p polarized light, S polarized is light basically vertically polarized light or plane perpendicular light. Um, so if the light consists P and S both polarization, in the reflection we will get only the S polarized light. And there are some like proof that the reflected and transmitted ray are at 90-degree angle, uh, and the Brewster's angle is basically theta b is tan inverse into by n. So we can see that how that turns to zero from the Fresnel's equation point, and I have discussed two question corresponding to the Brewster's plane, and also we have also discussed pulsed laser and how CW laser works, but basically we discussed the optical pumping portion. Then optical pumping is can be done using the conventional source and also using laser. So in the conventional source, have seen that the pumping, like the pumping alignment can be done by side pumping or end pump. So for solid and liquid, yeah, to use the conventional source, it's okay. But for gaseous medium, if you use the conventional source, you are not going to get any lasing action. And why is the reason? Because uh, you see that for conventional light sources, they lack the light rays lack they are actually not coherent, and they are very much random, and they can skip the actually basically not they can skip, actually the gas molecules can skip those light. So the main reason of doing the pumping is to send this gas molecule or ion or atoms to their excited state. But if the light ray cannot hit that gas molecules or atoms or ions, then pumping won't happen. So that's the reason we needed optical pumping by laser for gaseous medium. So, so some of the concept I have already discussed, that previous class actually has been discussed in this week's content. So I'm going to repeat those things. By the conventional light source have been discussed in the previous week's classes and also in the tutorial session. And I have also discussed topical pumping by like lasers also in the previous tutorial section. So I will do that. So here I'm using the picture from the study material physically, uh, which has been given in the lecture section. So basically, we have obviously that using the conventional light sources produce a very much very light laser and you can pump with such light. So if we use laser for like access media, it is to move that very negative of laser from laser which can excite the molecular or species. So do this like the different kind of lasers. So here, this founding method, uh, so to couple the laser, the being three, and it's not reaching M1. So in that case, we need our requirement basically is that it three is to achieve basic action. Our requirement is that M3 and only reflect level 1. So level can go to the other mirror. It's go back and it can go back and forth between the cavity and another one is a on the mirror. It doesn't need to go back and forth between the cavity. It is on this and one. So I ordinary dialect uh, can no use of us. We need a mirror that can transmit one level and for that you use like so this is like mirror. So in the last class I have drawn this diagrams by my hand. Uh, it's not that good drawing. So I it's just been provided in the lecture notes. So here electric mirror. The place I would not have that the mirror three is about so from this area, but allow me allows camera to go to reach mirror in one the desired output wavelength from the actual place. The boundaries are not actually basically I laser to make laser so very use that like that laser to achieve a lasing action. So this is the other laser is different. It can be same also. Like there can be the kind of but in the laser it's not that but when we use the problem so safe is the laser making is the but there are lasers in the that was or two different so the diachromatic mirror allows to turn light at the wavelength lambda 2 the complex cavity leading to the concept of the lasing. Thus, we see the operation from as visible but in that case The thing is that the dynamic mirror is very prone to damage because it has a very low critical damage threshold. So we need a optical material so that can be high optical damage threshold, and we can like when we are saying that diacritic reader has very low optical damage threshold, that means we cannot operate it continuously or with very high power pump laser. Basically, the thing is that. So for that, we need a optical thing that can do that work that it is going to couple the laser to that something kinetic, but it doesn't get damaged. So, so the cost of the laser building doesn't rise up, or understand that they can actually think that okay, we're going to get damaged. The dynamic is very, like, can say, very expensive to replace. Alignment, the laser action alignment, not only any optical action, be it the round spectroscopy and another spectroscopy, the alignment is very crucial. So it's not easy to replace a dichroic figure after some years. So we need permanent solution. And this is like now it's very cheap, but you know that helical laser do the basic necessary things. So now lasers are being used for detective complex research, defense system, medical system, and all. And those lasers and in general those systems are pretty expensive. So we need a very good reasonable fix. So for that we use basically a booster plate. And when we use booster plate, we just not only overcome the situation, like instead of dielectric mirror, we are using dichoric mirror to let the lasing actions to start. But dichoric mirrors are very expensive and has low optical damage threshold. So when we use boosted window, also we like have a sustainable option for a very long time lasing action, because it's the doesn't get damaged so much. And also the other thing we are getting, that we are getting a polarized light. So the booster angle, basically this graph shows the reflectivity with the angle, and uh, around 58-degree angle in the air, booster reflection happens. So what happened at that angle, polarization of p polarized light becomes 0 at the reflected beam in the reflected beam, but the s polarization beam still there. So when you place the Brewster window like this is the basically the like normal from the plane, and this is the theta b. So here basically the from the so the spontaneous photons emitted by the medium, so the medium when emit the spontaneous photons, uh, it acts as the seeding of the pumping. And what happened that this light when falls in this Brewster window, uh, so the at the Brewster window, what happens that p polarized light get transmitted and reach M1, and S polarized light also reach M1, but it also get reflected and transmitted. So the rise in the number of the p-polarized photons in turn result in their further rise through the simulation, and the positive regenerative effect will cause the buildup of the p-polarization light in the cavity, and they will be completely devoid of s-polarization. And for this effect, one way when you put a booster in window at this, the one effect is you are like you like avoid the dichroic mirror problem, but you also get a p-polarized output in this process. And by the same using the same Brewster window, you can use a linearly polarized light pump laser here. So we can overcome the issue of the dichroic mirror here, and also the we can dispense the dichroic mirror here. So the optical pumping scheme through one of the N phases. So we are using the N pumping, and this is again the normal, the phase of Brewster's plate. And we are launching the pump laser at the angle of Brewster angle. So basically the S polarized light get reflected and transmitted, but p polarized light get only like transmitted. So the S polarized light are pumping the active media, and we are getting first spontaneous emission, then stimulated emission. The polarization from the laser is basically random, first random, but by the virtue of this Brewster window, only p polarized output gets survived out of this out of the light produced by this active media. And using this booster plate, first of all, we can dispense expensive and delicate dichroic mirror. Second, that we can generate output power. And a bonus tip is we can get polarized output gain. Then we can come to electrical pumping. So for CW lasers, this is the scheme. Electrical pumping for CW lasers. So the mechanism of transferring energy is similar to that of a fluorescent light source here. The stray charges, primarily electrons, get accelerated due to the impressed field, gain kinetic energy, collide, and cause further ionization, resulting in a glow discharge filling the entire volume of the gas enclosed in the dielectric housing. And they collide with the atoms or molecules or like ions. I should not say ions, like you later will know that this electrical discharge first make the ions, then those ions get pumped by this electrical pumping. So the electrical discharge first make the ions, but they don't make atoms and molecules. They are already present in the medium. So the inelastic collision that the electron undergoes with the gaseous species, causing their excitation to higher level of energy, are essentially the mechanism of electrical pumping of the laser medium. So to enhance the pumping efficiency, we sometimes like mix the lasing gas with one or more surrogate gases. The case we will see in the helium neon laser. Species. or pulsed laser. The schematic is like this. And here, instead of end anode and cathode, we get uniform electric fields because of the high operating pressure that inhibits the occurrence of a glow discharge, and the breakdown voltage of the discharge gap increases and affecting a longitudinal discharge. So in that case, we need the uniform uniform field electrodes at the site pumping arrangement. Advantages for this arrangement is it brings down the breakdown voltage, though the number two is the voltage requirement from the um, power supply also brings down. And three, the um, so the discharge to encompass significant volume of the available gas. Now we have discussed the efficiency or operating efficiency. Operating efficiency is basically laser power and the input power given the input electrical power. So that is basically pump energy, the percentage of electrical power uh, converted into pump energy, then from that pump how percentage has been excited, and then if uh, the percentage is of that excited energy goes into heating, so the efficiency, operating efficiency will be that much, where the quantum efficiency is 1 minus d by 100. And the electro-optic efficiency is basically the efficiency of the conversion of pump energy, which is electrical in nature, equally 100 into 1 minus d by 100. So laser can be different types. They can be categorized based on the physical state of their active medium. based on the physical realm. They are basically gas laser, liquid laser, and solid state lasers. So on the base of their pumping method, laser can be divided as optically pumped laser, electrically pumped laser, chemically pumped laser, and gas dynamically pumped laser. And on the basis of the wavelength of their emission, of their emission, they are termed as infrared laser, visible laser, ultraviolet laser, vacuum ultraviolet laser, and so on. So on and so forth. So, and there are other kind of work laser, that fiber laser, solid state laser, excimer laser, free electron laser. The free electron lasers are very important. They can generate photons in like 10 hertz in there also. So on and so forth. So here We'll first discuss the gas lasers. So, gas lasers, very different that they can be atomic gas laser, where the lasering action has been done by pumping the atomic atoms of the gas laser. Ionic gas laser and the molecular gas lasers. So, fast gas lasers was the helium neon laser, 1960. Was helium neon laser. And in 1960, it has been developed. So, from that 1960 and today, 2026, researchers over the years have literally discovered thousands of new living transition in a wide variety of gases spanning across a broad range of electromagnetic spectrum. So, and only few are beneficial from the point of view of application. Uh, Once the helium neon laser was indomitable in that field, but till date, that a helium neon laser is indispensable because it used as an alignment laser. It is cheap and it does the work. And carbon dioxide laser are also there. They can operate in the infrared and use in industrial and medical laser. Uh, and excimer lasers are also gases, but they don't act as gas laser. So here we like conventional gas laser we are discussing. So that's the thing. So in the atomic and gas laser, we will get only electronic energy levels. The occurs between electronic energy level, where in molecular gas level as well as electronic, vibrational and nutritional uh, energy levels are also there. So here what happened that this is the ground state. Form the atom from ground level to level 3. Then the lasing action happen here between E3 and E2, and this is the thermal energy. Okay. Up to here as a non-radiative energy, the lasing action is here. So we cannot see it as a conventional three-level laser system. It is not also four-level laser system because it can be many-level laser system depending on the pump energy, and it can go up to E4, E5. Like one molecule can go up to E4, one is E5, and so on and so forth. But they will come back to E3, and it can doesn't need to be E3 all the time. It can be anything. It's only a general schematic. To 1 by n square. Pump energy is E1, and like global absorbed energy is the thermal, which is E2 minus E1. One. So the quantum efficiency is basically the lasing action happens E3 minus E2. So the quantum So here the lasing action in helium neon laser, like lasing happens in the neon atoms, but it happens with the help of helium atoms. So this is the energy diagram of helium atom. and that is helium atom. So this is the 3s1 layer, and this is 1s0 layer. So we can get 3s1 is basically this number come from 2s plus 1. S is basically s1 plus minus s2. So that s is basically 0. Here is 1, but when 1 is 0, so this is the small s actually. So it is have been written as like this, and this is the principal quantum number. So it's actually n. So this is a spectroscopic term basically. So we are discussing the atomic laser first, then the molecular laser, because to understand the energy levels, we also need to understand the molecular spectroscopy. So this is atomic spectroscopy. Basically, each level has been denoted like N, which is a 2s plus 1 Lj. So it can be 0, 1, minus half, plus minus half, only two options, 0 and 1. But for molecule, it can be 3 by 2 also. Sometimes. So what happened that the laser operates by striking an electric discharge in low pressure gaseous mixture, comprising 5 parts of helium and 1 part of neon. Okay, and it has to be in low pressure, in low pressure. Here, the helium create and maintain population inversion, and neon take parts in the lasing action. So the second orbit here is split into two sub level. That is 1 is 0 and 3s1. And why 1 is 0 energy level is up and 0? Because with each associated energy level, we also know the energy of that level. And when we discuss spectroscopy, we don't need to know the actual energy level, but which energy level has more energy than the other. We know that we need to know that basic thing, and there are many ways to remember that, and many like scope in the spectroscopy course. Or if any of you have problem with or want to understand how these things work, you can ask in the comment or in the like discussing forums, so I can discuss that thing also. So the inertistic collision in between helium atoms in the electromagnetic ground state undergo with the electrons present in the discharge result in the excitation in both these levels, and so the helium atoms goes from the ground state to the upper state. Then what happened that they helium into S1 plus E less kinetic energy. That is step 1. In step 2, what happened? Step 2, of course, helium at S0 level, and S1 level goes into collision with neon ground state atoms. And that leads to move them into 5s state. In the 5s and the 4s state, and the helium atom goes to the ground state. Ground state helium atoms are again ready to go to the upper state, and then like this helium ground state atom can go to the state. So they move to 5s and 4s. After going to 5s and 4s, what happened? These atoms can go to 4p and give us 3.39 micrometer wavelength. The atoms in the 4s can go to 3p and give 1.15 micrometer. And the atom from the 5s also can go to the 3p, and that will give the wavelength of sub-micrometer, 0.6328 micrometer or 632 nanometer. And from that 3p, those atoms can come into 3s level, and 3s levels they relax to the ground level. And for the relaxation, narrow boat tubes are preferred here. And we can get milliwatt to 1 milliwatt to tens of milliwatt power from this uh, laser. And this is single longitudinal mode operation is possible. In the helium neon laser, if we choose the length uh, that way, so as I have mentioned that helium neon laser is used as an alignment laser, but that 1.15 micrometer uh, radiation here can use to measure the optical fiber transmission line, because that they have a very insignificant loss at this wavelength. Now we can that helium neon laser is an atomic laser. Atomic gas laser. Now we will discuss ionic gas laser. So that is argon gas laser basically. So again, it's better if I use the diagram that has been used in the lecture notes. So it is also a CW laser, and in the it is basically you used to generate UV and visible wavelengths. And it has more power than the helium laser also. So here the instead of narrow bore tubes, here ceramic discharge tube are used to dissipate the heat. And when it can be air cooled, or if it has increased power, it can be water cooled also. So the most popular wavelengths are basically here 458 nanometer, 488 nanometer, 514 nanometer, uh, 351 nanometer. This is in UV range. This is basically blue and green. This is blue light, this is green light, and this is bluish green light. Okay, so you can have a like in a two case, like you want multiple wavelengths at same, so you put the prism outside the cavity. Then if you put a spectrometer here, you will get lambda 1, here to get lambda 2, and here lambda 3, while all three wavelength emission happens at the same time. But if you want only one lambda 1, so you can put the prism in the intercavity, and only lambda 1 gets falls the surface as normal, and only one wavelength at a time, resulting in a single wavelength lasing, and lambda 2 and lambda 3 will fall off. Like uh, lambda, like after being dispersed by this prism, only lambda 1 falls on the mirror normally, lambda 2 at an oblique angle, so that goes out, and lambda 3 doesn't fall at the mirror at all. It goes out of the cavity. So basically it's up to your choice what you want to do. And we can have multiple longitudinal modes in this argon gas laser, and also multiple transverse mode, but we always prefer only 100 transverse mode for the simplicity of the schematic and all. So for a different transverse mode, we need high power laser basically, and this laser actually works in a okay. This laser basically works in like a 100 milliwatt in region. So now we'll discuss some quiz questions of previous year. Question number one. A conventional source of light can be used to pump the laser. Option A, only through its end. Only through its side. Both through its end and side. D, none of them. So basically, we have seen in the previous class that a conventional light sources, the lights are not coherent at all. So the best practice is to use as a side pumping. For the end pumping, the overlap at first it is not a coherent light source. So the light uh, rays can go here and there, and for pumping it needs to be there needs to be a collision uh, between that photons and the atom. So the maximum chance of going with having that collision is to when it's only through its side. So question two is a dichroic mirror. Option A blocks one wavelength and reflects another. B blocks one wavelength and transmits another. Transmits both the wavelength transmit one wavelength and reflects another. I know. So we know that's the our option, that it transmits one wavelength and reflects another wavelength. Hydrophilic mirror is more prone to optical damage inside the cavity because it can intercept the nodal plane. B, it can intercept the antinodal plane. C, such overlaps are inconsequential in none of them. So what happened inside the cavity, like the waves are going to and fro. So because of this reason, they are forming standing waves that we have seen earlier. So these points are nodal point. So intensity is zero at these points. But these are antinodal point. This thing is not like that. And like the here the mirror, two mirror are basically the two nodal point. This point is nodal point. This is nodal point. So then nodal points are a zero intensity, but the antinodal ones have maximum intensity. And these nodal antinodal points can damage the dipolic mirror, and it is the reason it can intersect that it can be prone to damage to optical. It can be prone to optical damage. So it can intercept the antinodal layer because between the cavity, it can be placed here. We don't know how the standing wall will form. So at the face of the dipolic mirror, the antinodal point can be formed. Question 4 is conventional sources of light are generally inefficient in pumping active medium because they emit light over a wide spectral range. B is emit over a very narrow spectral range. A low intensity source, that is also true, but that is not the actual reason. Even if we increase the intensity, it will be not as efficient as laser. And we know that I have already said that the conventional source of light, they emit a broadband spectral range. So only for the lasing action we need a narrow, even a narrow spectral range will work. So we don't need a broadband spectral range. So this is the answer, emit light over wide spectral range. That is why they are inefficient. Question number 5. Which one of the following option is incorrect about lipoic mirror? It is expensive. It separates two different wavelength. Through reflection and transmission, which is also true. So it is expensive, that is true. There it separates, that is true also. 3 is it is a kind of dielectric coated mirror. Yes, it is kind of dielectric coated mirror, but not exactly, but it's not entirely true. Four, it polarizes the transmitted wave. That is entirely false. It doesn't polarize the transmitted wave. So this is the incorrect answer. Question 6. Uses the following optic beam rays to polarized output from a laser. Intercavity diporic optics. It doesn't give diporic optics doesn't give rise to polarized output. We know that. Intercavity transmitting optics at Brewster's angle. Actually, it does because it transmits the depolarized light. Transmitting optics in non-Brewster's angle that doesn't give it. So this is the answer basically. Brewster's angle. So transmitting optics at non-Brewster angle cannot give rise to polarized output from a laser because you know, at Brewster's angle only one polarization gets accepted or chosen. So that's how we get only the polarized output. Intercavity nonlinear crystal, intracavity nonlinear crystal. So intracavity nonlinear crystal can give rise to two polarization state from normal ray, but it doesn't only give one polarization. So that is not actually an answer that intracavity nonlinear crystal uh, will give a polarized output. Like not only by nonlinear crystal, it needs another uh, other things. Question number 7. Why can population inversion cannot be created in neon by striking an electric discharge? Only in the gas. Options are due to short-lived upper level, B due to long-lived lower level, C due to absence of low-lying energy level, due to presence of no line. So basically, you can see here that the energy level of 2s is equivalent of the energy level 2s of the helium is equivalent of the 4s. So the energy mismatch between these 2s and 4s and 2s 0 and 5s is very minimal, and that has been compensated by the thermal dissipation. So this is at 3s. So you can see that energy levels of 1s 2s is very low line, and due to this reason electrons decay very quickly from those states. Sustain a population inversion, and then they can transfer the energy to helium atoms. So this is the reason. Question 8. If the quantum efficiency of laser is 40% and the operating is 20%, then what percentage of input energy gets lost? A 40, B 20, C 80, D 60%. So here the quantum efficiency is given, but we know that operating efficiency at the last efficiency, like the operating efficiency denotes what percentage of input energy uh, it gets converted into the lasing action. So rest of them is lost. So basically the operating energy is 20%. So this rest of the things like 100 minus 20, which is 80, so 80% gets lost. That is the answer. Question 9 is, if quantum efficiency of a laser is high, then the heat dissipation in the lasing medium the quantum efficiency is high, then the heat loss, lost energy is low. Then if the lost energy is low, then the thermal energy due to this lost energy is also low. So basically the heat dissipation in the lasing medium will be low. So high is not the option. B is low, low is the option. Independent of quantum efficiency, that is not true. D is none of the. Question number 10.
if the energy per pulse of a laser is T millijoule and the repetition is 50 hertz. Repetition rate is 50 hertz, mean the pulse repetition rate that each pulse is being repeated at 50 hertz frequency. Then what is the average power of laser? 1.5 watt, 150 milliwatt, say 15 watt. D 0.5 watt. So average power is basically energy per pulse plus repetition rate. Not plus into repetition rate. Wait, so energy per pulse is 30 millijoule into 50 hertz. So hertz is the standard unit, but millijoule is not. Joule is the standard unit, so that is 0.03 joule. 30 into 10 to the minus 3, and that is 50 hertz. That will be 1.5 watt. So that is option number A. That is the answer. So that is for today. So much, and I am ending this tutorial now.